So in the previous lecture, we have looked into how a program, which is nothing but a sequence of instructions, could be stored in a memory block. And we also understood that the role of a processor is basically to execute the program or the set of instructions and find out the result or whatever is the intention of that particular program that is stored in memory, right? And for doing that, we also sort of understood that the instructions has to be fetched to the processor instruction by instruction, and every instruction must be executed. The results, if it has to be stored, it is going to be stored, or if there is some display that has to be done, it has to be displayed, and so on. And the program is going to finish when all the instructions that are there in the program gets executed. Okay, so for execution of the program, we saw there are a few things inside the processor, the components of the processor. uh, First and foremost was a few storage, temporary storage, which are known as the CPU registers, which is indicated by this block 1. A collection of registers, it could be 8 registers, or it could be 16 registers, 20 registers, 32 registers, and so on. But a finite number, typically small number of registers, which are going to be used for temporarily storing the data or instruction, and doing some local computation, right? So often, I have already visited this discussion, like we have discussed this thing in the last class, but again I'm reiterating the role of the register. Suppose I want to do a computation like uh, a plus b, let's say we want to do a plus b multiplied by c, right? This is a very common example that might arise in your regular programming jobs, right? While you write a program. So if you look at it, we have to get a and b and store them in some registers, right? And when I compute the value of a plus b, that has to be also available in some register, right? Then only I can multiply directly with c, which is, again, c is going to be stored in a register, and I'm going to multiply c with the result obtained by doing a plus b. So now if I did not have enough number of registers, what could I have been what could I have done? I might have calculated a plus b, and the result could have been stored back in memory, right? And then I would again fetch that particular value, fetch c, and then do the multiplication. So there could be other complicated examples where I might run out of the temporary storage, and I am forced to transfer the values temporarily from these registers to the memory, and on demand, whenever you need them, bring them back, right? So there is always this trade-off about how large your register file is going to be, right? I might have too many registers, but that is also going to increase the complexity of the circuit. It is going to increase the cost, and as I also told you, the more the number of registers, the instruction set or the encoding of the instruction is going to consume more number of bits, right? I have done this discussion in the last lecture, where I said that if there are only 8 registers, you need only 3 bits to address one of the registers, right? And if you have a source register, one source register, 2, and a destination register, so it is going to consume 3 multiplied by 3 bits per register, so 9 bits, right? Whereas if you have 64 registers, for instance, you will require 6 bits to identify a particular register, right? So in that case, for these 3 registers, we are going to consume 6 into 3 is equal to 18 bits, right? But again, in a computer that has 64 temporary registers for local storage, which is very close to the ALU that does the computation, you can write programs that could take advantage of this storage, and your program can become much faster compared to a computer or a CPU that, let's say, only has 8 registers, right? And beyond 8, I will not be able to store any more values locally within the processor. That has to be swapped out to the memory. where all your data and the program everything is stored, right? So again, this is a trade-off. More number of registers is good for your program, but the underlying complexity of the hardware is more. The instruction encoding is going to require more number of bits, right? And of course the overall cost is going to be bumped up, right? Then we discussed about the ALU, which is called the arithmetic and logical unit. The arithmetic and logical unit consists of few circuits that are uh, specifically designed for a certain computation or logical operation, arithmetical or logical operation. So the arithmetic operations could be, as I discussed, addition or subtraction. Logical operations could be XOR, or let's say AND. You want to do a NOT or an AND or an XOR, right, and so on, right? So based on the control inputs to an ALU, which basically is a set of bits that identifies the operation that you are trying to do, an instruction is trying to do, the ALU is going to select one of these circuits, right? So if it has four circuits, let's say one for addition, one for subtraction, one for let's say and one for complement, not, right? So out of these four different operations that are possible on the ALU, how many bits is going to be required to indicate the ALU that what operation to perform? That will be log 4 to the base 2, right? 2 bits are enough to identify which one of the four operations it is going to perform, right? Similarly, if you have 3 control inputs, or rather if you have 8 functionalities in the ALU, then you can support that identification of the operation using only 3 bits, right? So that typically is called the opcode, right? We are again going to elaborate on that. So when you have I gave you a basic idea about how the machine encoding of an instruction looks like. Because when I write add a comma b or add src1 src2, this is just plain English, right? That is primarily meant for human beings to understand what this is going to do, right? So typically this is assembly code, and assembly code is of course not understood by a computer, because what you are seeing is plain English. This is going to go to a program called an assembler, which is going to compute or which is going to actually encode those assembly instructions in machine language. And this machine language is basically a specific bit pattern that is predetermined by the instruction set architecture. It is going to tell that, okay, the first 4 bits mean this, the next 4 bits mean this, the last 4 bits mean this, right? So based on how we design our instruction set architecture, this is going to be predetermined that what bits of the instruction, the encoded instruction of the machine code, means what, right? And the processor is going to understand that language and is going to act upon it, right? So we will look at a concrete use case while we design our very simple processor in the rest of this course, right? And apart from the register file and the ALU, we also have a few other special purpose registers. I named one of them called the program counter, which is by far one of the most important registers required to run a program. This primarily refers to pointer pointing to what is the next instruction that is going to be executed, right? Because as I told you, a program is nothing but a sequence of instructions, right? And let's say a particular program has 100 instructions that are going to be executed, right? Let's say you have written a sorting program which takes a memory chunk from, let's say, starting from memory address 100 going to memory address 200. You have 100 bytes and you need to sort them, right? So you have written a program, and this program is basically going to be consisting of instructions that are supported by your underlying architecture, right, or your ISA, right? And and that program may consist of, let's say, 10 instructions or 20 instructions and so on. So the program counter basically points to the instruction that has to be executed next. So you always start with the 0th instruction, which could be at memory location, let's say 10. then the program counter is going to point to 11, which basically means the first instruction is going to be executed. Then it goes to 12, which is the second instruction, third instruction, and so on, unless and until there is a change in the flow control, right? Suppose you call a function, so then there is a branching, right? Or you write an if else condition, so if something happens, do this, right? When you do, or if doesn't happen, you have to skip that and go to a different instruction, right? So those are some special cases that are going to be handled, and typically program counter, or the, you can also call it an instruction pointer, is basically points to the instruction that is going to be executed next. Okay, and apart from program counter, there are a lot of other registers which basically help the program to execute, right? As I told you, it is very much little about computation. Very little computation actually happens. As you can see, that ALU is enough for doing the computation, right? But most of the computer or the CPU design is primarily to move data around in a very intelligent way, right? Memory has most of the data, and the data has to be loaded to these registers, and within the registers data has to be swapped, data has to be moved into the ALU, moved out of the ALU, moved to the memory, and so on. There's a lot of instructions that have to do specifically with data movement. Okay, so that's why I wrote movement of the data. This is one of the fundamental requirement of your CPU architecture, the micro architecture, how data gets moved around. And of course there is computation, but as a matter of fact, there is not much computation, right? Not much sophisticated computation that an ALU is going to do, right? uh, it's depending on how many distinct operations the ALU can perform, but typically they are not a lot, right? Most of the complex operations that you see are typically implemented in form of a software, right? So software is going to make use of the fundamental operations that are available in the ALU and make complicated things happen. Okay, so I think this is a kind of refresher of what we have looked at so far, and as you can understand that this computation, movement of data, and other things like getting the instruction from the memory, moving it to the registers, pushing it to the ALU, and so on, all these things need some kind of a central orchestration. The program counter is getting updated, the program counter goes to the next value. This entire thing is not manually done, right? If you look at the execution of a program in step by step, right, we will revisit this thing to understand what the exact steps are, but at least for now you can actually kind of have some intuition that the program is executed in finite number of steps. Even an instruction, suppose you want to add let's say A and B, you need to understand, first of all you need to copy the instruction from the memory to the somewhere in the CPU, and then understand it's an add operation. You need to understand that, right? The CPU needs to understand that it's an add operation. Once it understands that add operation and not a not operation, because not requires only one operand, whereas add is going to require two operands, it is going to look at A and B, and A and B could either be registers, or it could be memory locations also, right? Depending on your ISA. So then once it interprets that A and B are, let's say, memory locations, those values again have to be loaded to the CPU registers. These are not parallel, right? You need to do sequentially for a simple CPU design. You need to get this value A and B, you need to kind of understand or decode the operands. After that you say that okay, I don't want to do an OR operation with A and B, I want to do an add operation. Okay, so this is the next thing that has to be done, right? The ALU computes this value A plus B. After you get the result, then the value has to be stored in a certain register. Okay, you cannot do this before the ALU computes these values in some random order, right? So this, if you see this entire sequence of this very controlled steps, right? What exactly happens in the CPU, what data is copied from what register to what place, next instant of time what happens, this entire thing, right, has a very tight orchestration and control, right? and typically this is done by one of the most important parts of the CPU called control logic. Okay, so roughly, so I would not say this is just 3, this is like 3, I would say 3A. 3A is a program counter, 3B is a let's say instruction register, 3C could be a decoder. There are many special purpose registers. There are some special purpose registers that help you to or help the control logic to flow. Okay, so we'll look at each one of these individually, and we will also implement them. I'll show you how to implement them in circuitverse. I have some implementations that has already been done by me, and I can show you, take you through the steps of how to implement it yourself, and kind of also appreciate the fact that we can make a very simple computer using the things that we learn now, right? And it is not going to be very complicated or a fancy computer that can execute a lot of things, but at least you can do basic arithmetic. Let's say you want to do, let's say 50 plus 7 minus 8 plus 9 minus 11, right? It's an expression. You can write a program to find out this value, right, in an assembly language that we define from our instruction set, right? That is going to give you a simple but complete knowledge of a simple processor. Okay, so as I told you, the first component was the register file, which is going to deal with data transfer among registers. Okay, so let me write. So primarily, as I told you, there is a lot to do with data movement. The data movement could either be register to register. So this register could be register A, this could be register B. This arrow actually means that the contents of register B is loaded to the contents or to register A. So the contents of register A now becomes what is there in the register B. Okay, so this is typically called register transfer. Okay, so you copy the contents of one register to another register. It's a very important operation that is required in the control of a processor. The other important thing that we also require is what this is basically either let's say some register X, and this is basically loaded from some memory. We have a memory from a certain address. Okay, so this is the address of the value in memory. So our memory, well, let's say, looks like this, as I have told you earlier, and let us say we have a memory location which is 0x50, and it has a value, let's say 1000. Okay, I'm not really talking about binary or hexadecimal and so on, just logically referring to them as some values. So the point here is that register X is going so to be loaded by this value 1000. So suppose if I do register X is, let's say, referred by X, let's say Rx, memory 50, right? So this means that whatever is the value in memory location hexadecimal 50 is going to be loaded to register X, and vice versa. You can also do it the other way around. It can also be that whatever is this content of Rx is going to be written to the memory, this memory location, right? So this is loading register, this is storing the register. So you want to store the value that is contained by a register to a certain memory location, right? So these three operations are extremely important, right? And there are some more some more things that you can do. Sometimes you want to write a particular value in a register, as I kind of mentioned about immediate operations, where I want to load register A with the constant 5, right? That is sometimes happens, right? You need to do that. Or you want to load the register with the value 0, right? Often we write loops, right, where I start I equal to 0, I is less than something, and I plus plus, right? So often we want to deal with these variables. Whatever variables you deal with in your high level programming language, you can imagine them to be equivalent to be stored in some form of registers inside the CPU when the program gets executed. Okay. uh, there are too many variables. Not all of them could be brought in at one go inside the CPU. There is some dedicated storage that is there, like stacks and so on, in the memory. You don't have to worry about that. But at some point of time, those values are going to come into the CPU. They are going to be manipulated and be back. Okay. So exact kind of operations that you do in the high level language are actually required to be executed inside the CPU, and typically with these register transfers. Okay, we copy variables, we do some arithmetic operations. Register transfers is something that you cannot avoid, and also the loading and storing, that is register to memory, or memory to registers, and register to memory. Okay. So now let us look at a little bit of how these transfers can take place, what could kind of combinational circuits we might have. So let us look at this figure where I have two registers, register A and register B, right? And I want to treat register A and B as my source registers. Okay, so I can call them as a source registers. Okay, and I have a register C which is my destination register. Okay, so the problem here is that I want to either do a register transfer B to C, or I want to do a register transfer A to C, right? So how can this information be written in terms of RTL? Here RTL stands for register transfer logic. This could be either written as C is my destination that gets loaded by A, right? This is one option. Or C gets loaded by B. Okay. So as you can see that depending on the value of that is presented on the, in the select bits, right, in the multiplexer, I can select one of two, right? And these registers have 4 bits, right? So all the bits, right, has to be multiplexed to the register C. So that's why we have quad 2 cross 1 mux, which quad means 4, right? And every register also has 4 bits. So I take the 0th bit of register A, I take the 0th bit of register B, and based on the select line, I want to choose one of them and put that in the 0th bit of register C. Okay, that's why it is quad 2 cross 1. But this operation, the transferring the 0th bit from either B or A and putting that in register C, is done by a 2 cross 1 multiplexer, right? 2 cross 1 because there are two choices, and this can be only one select line. If the select line is 0, I may be choosing register A. If the select line is 1, I may be choosing register B. Okay, so and you have to do it 4 times, or you have to do it basically using 4 pieces of the same hardware. So same for the first bit, right, where I take up the first bit and copy it to the first bit in the register C. Okay, so this is basically your this can be used to address the register. So if you have 6 registers here, you cannot do it by 1 bit. You cannot do it by 2 bits, because 2 bits can at most refer to 4 registers, right? So if you have 3 bits, then you can support at most 8 registers. Okay, so this is somewhat equivalent to addressing the source register. Okay, similarly you can also have multiple destination registers. You can also keep that in mind, right? And all you need to do is that again kind of demultiplex it right into one of the destination registers. Okay, so this is kind of important that you can have, let's say, n source registers and n destination registers. You have to make a choice of selecting one particular register and transferring it to the destination register. That has also to be selected. Okay, so now coming to the left part of the figure, you might see all these things, right? Let's say, what is this strange thing doing here? Okay, enable is just enabling the multiplexer, right? So there is nothing worrisome about it. I am always assuming that the multiplexer is going to be enabled when I have a load condition. And what is a load condition? Load condition is that when do you want to do the register transfer, right? This register transfer, as I kind of told you earlier, uh, is not going to happen all the time, right? So as I told you in this particular figure, there are some instances of time which is very specific. Only at those points in time you are going to do the register transfer, that is mandated by the control logic. The control logic is going to mandate at this point of time the contents of register X has to go to register Y. After that they should not talk to each other or even interfere with other register transfers. Okay, there's an isolated piece of time and at that time period this transfer has to happen. It cannot happen earlier, it cannot happen later, because as you can understand, whatever instructions we are going to be executing inside a computer has very strict timing limitations and ordering. Okay, I gave one more example, I think, in the last class, where I spoke about swap, right? Suppose you want to swap two registers, the contents of register X and the contents of register Y, right? What do you ideally do? You want to save the value that is there in the register X to some kind of a temporary register, right? Then write the value which is there in Y with the value that is in X, and then write back the value of the temporary register back to Y, right? So in this way you can do the swapping. But now note that you cannot execute this instruction in a random order. Okay, you have to first transfer the value of X to temp, right, and so on, right? Even if you change the sequence, your swap is not going to work, right? I gave this example because all of you are familiar with how swap operation occurs, right? So similarly, for executing more complicated instructions where there are a lot of things to take care of, starting from register transfer to updating the program counter to doing the actual computation to writing back the results, they have very strict sequences, right, in terms of time, which is taken care by the control logic. So the control logic is going to have some kind of outputs, right? These are often called timing states. Don't have to worry about it now. Um, which basically says that if in this particular circuit, if it is t1, which you can think of this as like time is equal to 1, or if it is t5, which basically means time is equal to 5 in some sense, right? In some modular sense, maybe the time only goes from, let's say, 0 to 10 and then it starts from 0 to 10 again, right? Maybe it's a mod 10 counter or mod 11 counter, whatever. So the states kind of tell me that where am I in 0 to 10, right? And only in those two cases, T1 and T5, I am going to enable this register transfer operation. Otherwise not, right? So otherwise what will happen is, like, if T5 is equal to 0 and T1 is equal to also 0, load, this output is going to be 0, right? The load is not going to be enabled, right? This is one example. You don't have to worry about this specific example. But what I am trying to tell, that there is going to be a condition for the RTL. The register transfer is not just going to happen just like that, right? We know how to do the register transfer in this way. It looks trivial, but what is more important is when do you have the register transfer? That is basically a condition that is going to arise from the underlying control logic. The control logic is going to tell, hey, register A, please transfer your register to transfer your data to register C. Okay. Other than that, you are also going to have this addressing uh, based on, again, on some kind of a condition. You are going to issue a certain address, right? Let us take this example of the swap, right? You can think about it. Let's say I want to swap the contents of register A and register B using register C as the temporary register, right? So this circuit is definitely not going to work, because here I only have a one-way transfer from A to C or B to C. In in the case of swap, I also have to write from register C to B or A, right? So that also has to be modified, right? So this circuit has to be modified. You are encouraged to think about it, right? That will give you a lot of clarity, right? So the exercise that you must do is that have a very small circuit using multiplexers. You don't have to worry about the all this enable and so on, right? All you have to do is that there is a set of conditions. There are three steps to do the swap, right? As you know, I'm not going to repeat that. So there are three register transfers and they are strictly ordered in time. You can call them as three timing states, let's say T1, T2 and T3, right? T1, what happens? T1, you can initiate the discussion. The T1, you basically copy A to temp, right? The contents of A has to be transferred to the temporary register, which is the register number C here. T2, something happens. T3, something happens, right? So you can start imagining what kind of form this circuit might take, right? And think about it, right? Try to design. If there is any confusion, you can ask. Okay. Now let us look at also the scalability of this kind of a register transfer. For example, here I show you three registers R1, R2 and R3, right? So there are 6 data paths and each register requires a multiplexer to select in between two sources. So if R1 is going to send the data out, it can either send it to R2 or it can send it to R3, right? In this particular case, the register requires to multiplex this value either in between these two sources, right, where it wants to send. And if the register consists of n flip-flops, then there is a need for 6n lines and here 3 multiplexers. Okay. So as you can see, as the number of registers increases, the number of interconnection lines and the multiplexer increases, right? So very broadly, if you have in such registers, right, you have to have sort of NC2 links in between them, right? And you can always have twice the number, sometimes because of the direction of the transfer, right? Sometimes it could be a direction from register X to Y. You can have a separate path from Y to X, right? So this will be 2 times that than that. So definitely it is quadratic in terms of the number of registers that are present inside the system, right? So this is definitely not a very good architecture to scale the system, right? Because as I told you, for many processors, you might have 30-40 registers inside the CPU and inside the register file. And if you need so many interconnections in between the registers, it sometimes becomes a difficult task to wire them all, right? You need to basically have these wiring lines which are connecting the individual registers, and this, as you can definitely see, I guess it's not going to scale very well. Okay, so although it has some pros and cons, because it has some I mean pros where as you can see, all the lines are independent, right? So if R1 is sending some data to R2, at the same time R3 can send some data to R4, right? Because you have independent lines and they are not going to conflict with each other, right? But what we are trying to say, can we cut down on the number of lines? Of course we will lose some flexibility, but the overall complexity of the inter-register wiring is going to be more simple. Okay,